All right, so welcome to Probability and Measure, lecture number 4, the minus 20 degree edition. In this lecture, we'll be discussing one of the most famous of all the measures, Lebesgue measure, named after Henri Lebesgue, the famous mathematician of the early 20th century. Lebesgue measure is simply the length of an interval. That's basically it, but it turns out that there's a lot more going on here. What else can I measure the length of besides intervals? Find out in today's lecture. Welcome back to another lecture of Statistics 571, Probability and Measure. Today we're going to do something special. We're going to talk about the one and only Lebesgue measure. I say one and only because it is unique, and we're going to prove that today. It's a big piece of measure theory, and it allows us to extend many ideas that we have, things like the integral, which we'll be talking about in the subsequent lectures. And it also is going to allow us to define things like probability distributions and density functions, in the real numbers, that is, and in Rn, I guess. So regardless, let's jump in right to that and start talking about Lebesgue measure. Right. So first of all, Henri Lebesgue was a famous mathematician. Apparently he was around in the early first half of the 20th century in Paris, kind of until he died, I think, in 1941, which when I read that, I was thinking to myself, Nazis? But yeah, it turns out it was complications of tuberculosis, so maybe healthcare wasn't so good in Paris under the occupation. Can't say I know much about the history. Regardless, Lebesgue measure is a central point of measure theory, so let's talk about that. The first thought is, well, let's say we start with omega being either, say, the unit interval, which is half opened, half closed, or we could just take omega to be the real line. Either can work. We could take other intervals, of course, but these are going to be the two of interest. And effectively what we want is, we want lambda, a measure of an interval, a, b, to equal, well, b minus a, the length of the interval. So, okay, that's not that interesting, right? It's just trying to get the length of an interval. But the idea being is that now we can use these tools that we developed in the last two lectures, Carathéodory extension theorem, the uniqueness of the extension based on Dinkin's pi lambda theorem, and we can use that, right, to take this simple idea of assigning lengths to intervals and extend it into a vast family of Lebesgue measurable sets. And that's what we're going to do. So, what do we need to do? All right, so for now, we're going to say lambda is a pre-measure on the set A, script A, which is going to be where script A is any subset. Nah, it's not going to, it's easier to do it this way, is any finite union of half-open intervals. So, for example, we could have something like A, B, union, C, D, where in this case we would have A less than B less than C less than D, or otherwise it, wouldn't be as interesting. Right, so the idea is we're going to start with this set A. We're going to take all the half-open intervals, and we're going to take finite unions of them. This is going to give us, I think, a ring, if I'm correct. First of all, it's definitely a pi system. That's the first thing. So first of all, the claim A is a pi system. Recall from the last lecture that a pi system basically just means I can do intersections. And the nice thing is that, I'm not even going to write proof. I'm just going to basically point out that if you take A and B and you intersect it with C and D, then this could equal a couple different things. Well, one is it could equal the null set if either, I guess in this case, B is less than C, or I guess we could do it the other way, which would be what? D less than A. Or what it might equal is it might just equal something like C comma B if, in this case, A is less than C is less than B is less than D. We can keep doing more cases, but the point is that we're going to get out a half-open interval here. If we intersect two half-open intervals, we're going to get a half-open interval, or we're going to get the null set, which means we have a pi system, right? And then if we take finite unions of half-open intervals, we can still intersect them and get another union of half-open intervals. Just for the sake of completeness, I'm just going to write this. Let's see if we can figure this one out. This would be if A is less than... if C is less than A is less than B is less than D is less than B, if I got that right. I'm kind of just doing this off the top of my head, so I might have gotten the inequalities right. But the point is, we could actually draw a picture of this, and we could have something like A and B, and then we could have another one, which would look something like C and D, and then the intersection is simply just this guy. Though I used the same color as the axis, so it doesn't look very good. There we go. We have a lot of colors to work with, so I might as well use them. Right, so that's just the point, is that we have a pi system. Easy, right? That's not so bad. And that means we can use this, right, with the theorems that we had last time. We have another claim. And the claim is that A is a ring. I think, I wrote down in my subnotes here that, my footnotes, I guess I should say, is that in Dudley's textbook, he considers just half-open intervals, not finite unions of half-open intervals. In that case, you don't have a ring, you have a semi-ring, but then you would have to do Carathéodory's extension theorem for semi-rings, which I didn't do in this class, but the point is there are different ways to construct Lebesgue measure. This is just one of them, and it seemed to make the most sense. Or at least it was kind of the easiest one I could think to include in these lectures. Anyway, I'm going to double check the definition of a ring, because I always have to remember which is a ring and which is a field and whatnot. So, right, if we'll say recall, a ring is has the empty set and is closed under, I think it's set subtraction and unions. Set subtraction and finite unions. Great. Well, then A is definitely going to be a ring, right? Because, well, first of all, we can check the first thing, which is that if we have little a equal to B, then this thing is going to be defined as the empty set. It doesn't really make sense to write a half-open interval like that, because it's like saying it contains A, but it doesn't contain A, so I don't really... It might annoy some very pedantic people, but roughly the point is that if we take the left and right endpoints in one of our intervals to be the same, then we can just say that's going to be like the empty set. Or we can just say the empty set is in there, because why not? We're constructing it ourselves, so we have the power. For set subtraction, you can just notice that if I take a half-open interval like AB, and if I subtract from it another half-open interval CD, then once again, kind of like what I was doing up above with intersections, well, there's only a few possibilities, right? We might just get A and B out again, or we might just hack off part of this and end up with something like AC closed, or we might end up with D open, B closed, depending on if A is less than C or whatever, right? I'm not going to write that all out, but the point is that we can do set subtraction, and we have and still remain in the set A, so we're closed under that. And lastly is, finite unions. That's kind of by definition, because I already defined A up above as being any finite union of half-open intervals. So if I have a finite union of half-open intervals, and I union it with another finite union of half-open intervals, then what do I have? A finite union of half-open intervals. Good stuff. So basically, there's not even anything to really show for the last bit, but it's just by definition. Anyway, the point is that this set A that we constructed is going to be both a pi system and a ring. And that means we can use this with some of the theorems that we had from the last class. So there's a couple other things we have to talk about. First is the famous Burrell sigma field. So I'm going to use script B throughout this course to refer to the Burrell sigma field. If I'm correct, and I kind of forget, I have to double check the Wikipedia page. I'm pretty sure Emile Burrell was Lebesgue's supervisor, and also living in Paris in the first half of the 20th century. So probably interesting pair there of guys. Anyway, the Burrell sigma field, which we could define the Burrell sigma field in some sense in any, I guess, topological space, because it's based on open sets, but we'll do it here. I say that with an asterisk because there's so many weird little corner cases in mathematics that there's probably cases where trying to define such a thing will fail. But we're going to stick with nicer settings in this course, so we could define, say, the Burrell sigma field on the reals, which is basically a sigma field generated by open sets. So when someone says Burrell set, what they mean is that I'm starting with all of the open subsets of some space, the reals, the Rn, right, omega, whatever omega is, and I'm going to take those open sets and I'm going to sigmify them. That is, I'm going to create a sigma field based on those sets, and that is going to be the Burrell sigma field. Any set in B is going to be a Burrell set. So why am I talking about this? Well, we can generate, or B from this finite unions of half-open intervals as well. I'll say that is, maybe that was a silly sentence to write, because basically what I'm saying is that the Burrell sets are going to be the sigma field generated by A from above. So if I take all of my half-open intervals and I sigmify them, I get the Burrell sets. Cool. So And this could be, again, for the unit interval. It could be for the real line or whatever else we want to work on. So this is the Burrell sigma field, but we have something else in contention. I'll say we also have m lambda, which is going to be the set of all Lebesgue measurable sets. So then the question is, well, are these the same thing, right? So this leads to a question. Is the Burrell sets equal to the Lebesgue sets? Well, no. The answer is no. Yeah, furthermore, we have that actually the answer is that the Burrell sets are strictly contained within the Lebesgue, the set of Lebesgue measurable sets, which itself is a sigma field. Oh, I lost my pen. Hopefully it's still working. Anyway, it actually turns out that, I'll say, in fact, the set of Lebesgue measurable sets is the completion Spelling and math are kind of mutually exclusive within my brain, so there's probably going to be plenty of issues in these written notes. Anyway, it's the completion of the Burrell sets with n lambda. And if you recall the notation from the last lecture, n lambda are going to be the Lebesgue null sets. That is, this is going to be any subset of, well, the real line. Let's say if we're working with R, like at the top of the page here, any subset of the real line that has Lebesgue measure of 0. Strictly speaking, we would want to say Lebesgue outer measure. I'm kind of being a little bit sloppy here and using lambda both as, well, the length of an interval, but also as a pre-measure, but also the outer measure as well. Based on that, which is just Lebesgue measure. So, yeah, you know. Well, I guess strictly speaking, the outer measure would apply to any subset of the real line, whereas Lebesgue measure itself would just apply to Lebesgue measurable sets, M. And that's the next question. Is every possible subset of the real line Lebesgue measurable? No, it isn't. And we're going to get to that. But before we get to the idea of what's Lebesgue measurable and what's not Lebesgue measurable, we have to mention one other thing, which we'll say point of interest, which is that the Lebesgue measure of the interval, as the half-open interval that I started with, is going to be b minus a. Okay, that's not very interesting. What's interesting is this is basically lambda is the only measure that does this, to be highly imprecise in my language. That is, lambda is the only measure that's going to assign the length of the interval as what we think of as the length of an interval, the right endpoint minus the left endpoint. Why is that the case? Well, this comes right back to uniqueness and the idea of the Dynkin pi lambda theorem. So let's go through carefully and just kind of talk about how we can use the theorems from the last two lectures to get to this. So step 1 is that lambda is a pre-measure on a ring A. Okay, step 2. Carathéodory says that lambda is a measure on the sigma field generated by A, which happens to be the Burrell sigma field. Step 3. Uniqueness. Well, let's just say A is a pi system. A is a pi system. Therefore, for any measure mu that assigns the length b minus a to a half open interval b minus a, mu coincides with lambda, Lebesgue measure, on on the Burrels sets. So this is really just using what we talked about in the last lectures. The fact is we can start with these half open intervals, we can extend to any Burrell set, then we can also show that this is unique. And in fact, if you have a measure that's going to be assigning the length in the usual sense to an interval, it's Lebesgue measure, and that's the only one we get. And furthermore, we can even do this in higher dimensions. We could do this in, say, Rn if we wanted to, which we'll talk about a little bit more later in this lecture. But now we got to talk about the next topic. So the next topic is, are there any, let's say, sets A subset of the power set of the reals? I'm not going to use the reals. I'm going to use the unit interval. But the thought process is kind of the same. Such that A is not Lebesgue measurable. And the answer I kind of said already in this lecture, it's yes. And that's going to lead us to the Vitali set, which is the next topic. So in general, there are multiple different constructions of non-Lebesgue measurable sets. They're all kind of crazy. We're going to stick with one of the maybe most classical ones, the so-called Vitali set. You can find it. I'm pretty sure I put a link in my notes here. Yep, there's a Wikipedia page on the Vitali set, so you can read more about it there if you want. So we're going to say example, the Vitali set. There are other ones as well. They're super hard to visualize in your head. Try not to think about them too much, or else it might cause blindness or blood streaming down your eyes. They're pretty horrible to think about and look at. That being said, let's construct it, right? So what can we do here? Well, we're going to start with omega being the unit interval, the half-open unit interval, just because it's easier to work with it like that. And then for x and y in here, we define addition. We'll say mod 1. What I mean by that is that if we add two numbers together and we get something greater than 1, we wrap back around to 0. and do it again. You can think of this as like taking the unit interval and turning it into a circle, right? Kind of taking 1, wrapping it all the way back around to 0 again. Mathematically, what I mean by that is, more formally, I should say, is that x plus y is going to equal, well, just x plus y in the usual sense, if x plus y is less than or equal to 1. I mean, strictly speaking, I should probably use something like circle plus, but I don't really feel like introducing additional notation, so we'll just write it like this, and I think it should be straightforward as to what I mean. All right. Visually, what we're doing, as I mentioned, is we are taking the unit interval and we're kind of wrapping it around on itself. So we start at 0, maybe 1/2 is up here, and then we get back at 1, and then we just keep going around in circles. All right, so then where do we go from there? All right, so what we're going to do is we're going to define, let's switch back to black. We are going to define L, script L. Whenever you see script L, it's probably going to be a lambda system, but we haven't gotten there yet. We're going to define script L to be all to be, to contain all Lebesgue measurable, let's say, sets A contained within this unit interval such that lambda of A is equal to lambda of A plus X for any X in this unit interval. Maybe I should just write omega, but we'll just keep doing that so we're trying to make it clear. What do I mean by saying A plus X? Where we should define this, A could be just some subset of the unit interval, so it's a set. X is a point. I define A plus X to be the collection of points Y in this unit interval such that Y minus X is in A. Okay, so that's when it's mathematically precise. What are we really doing intuitively? Basically, A plus X means shift A by X. So if A is a subinterval of that unit interval and X is some number, then we're just kind of shifting it a little bit to the right. Because of the way we define addition here, we would wrap it back around if any points cross the, 1, the boundary at the point 1, we would just wrap it back around. So you can think of it as just taking an interval and shifting it, and if I fall off the right-hand side, I just come right back on the left-hand side. Right, so what are we going to do with that thing? Well, the first claim, so the claim is that L is a lambda system. That one L leave for you to check at home. Just go back to the definition of lambda system and see if it, holds for sets A. It's not the most exciting thing to do. It's just really checking the definition of a lambda system with respect to sets A that are shift invariant with respect to their Lebesgue measure. Now, so since A from above is such that script A is contained in L. So what I'm saying here is A is going to be the same thing we had above, which is the finite unions of half-open intervals, in this case being subsets of the unit interval, not the real line. And the claim here is that they're contained in L, that is, they're shift invariant. And this kind of makes sense, right? If I have an interval a comma b, and I shift it a little bit, well, the length of it is still going to be a comma b. I mean, we can write this out exactly, I guess. Right? If we have, let's say, lambda of a b is just going to be b minus a, and lambda of a b plus x is going to be, well, lambda of a plus x, b plus x, and this is just going to be, well, b plus x minus a plus x, which is just b minus a. Now, strictly speaking, we could have wrapped around if we cross 1, so we'd have to be a little bit more precise, but I think we can kind of just hand wave and say circle, right? It's still the same length, even if it gets cut off between the 0, 1 boundary. So yeah, basically the point is that the set A that we started with is contained in L. L is a lambda system, and that means, let's go back to black, therefore, the sigma field generated by A, which we said already is the Burrels sets, is contained in the lambda system. This is Dinkin pi lambda theorem from last time. So it's quite a nice theorem, actually. It's when you first see it, it's like, well, wait, why am I defining pi systems and lambda systems? It's kind of annoying to have all these extra definitions floating around, but really useful because suddenly we know that, every Burrels set is now shift invariant with respect to Lebesgue measure. That's pretty cool. So I'll write that out just so it's clear. Every Burrels set subset of, let's say, of this unit interval is shift invariant with respect to lambda being Lebesgue measure. I guess we have a little bit of a double usage of lambda systems and lambda being Lebesgue measure, but I think it should be clear from the context that, well, I'm either going to write a lambda system, and that's the only time that lambda will show up. Otherwise, lambda will always be Lebesgue measure. All right, so that's pretty cool that now we have that this is translation invariant for any Burrels set. How can we use that? Because remember, our goal in this section is to construct the Vitali set. That is, we're trying to construct something that's non-measurable. So the next thing we need to do, next, we say that x tilde y, this is an equivalence relation. So we're going to define, I shouldn't say that in this section we're defining an equivalence relation. X is equivalent to y if the difference between x and y is a rational number. So, for example, let's do green. For example, if I have something like, well, it has to be within the unit interval, so I guess I need to make sure that it's not, I have to make sure it's small. I guess we could have something like 1 over the square root of 2 and 1 over the square root of 2 plus, I don't know, some small number, like 1 over 100. These two would be equivalent because their difference would just be 1 over 100, which is a rational number. If I had some other irrational number here besides 1 over root 2, then I would run into trouble. because I wouldn't, the difference between them would not be a rational number. So this is just a way of defining an equivalence class. What this means is that, therefore, we can decompose this unit interval into disjoint equivalent classes. So basically, we're taking the unit interval and we're cutting it up into a lot of sets. In this case, I guess it would strictly be, uncountably many sets, right? Because it would be the same cardinality as, like, I think the irrational numbers, which would be uncountable. Uncountably infinite. But regardless, the idea is that we're taking this unit interval, we're cutting it up into an infinite number of pieces. Each of these pieces is going to be disjoint from the other pieces, right? Now, we're going to define a new set. Define H to be a subset of the unit interval such that H contains one element from each equivalence class. So what that means is that, okay, we have the unit interval, we break it up into a bunch of disjoint equivalence classes. Now I'm going to go to each one, and I'm going to take one representative element, and I'm going to stick it in H. So I'm just going to go grab one, put it in H over and over again. Can we actually do that? Yes, if we assume something called the axiom of choice. We can do this if we assume the axiom of choice, which will lead us down a dark and dangerous rabbit hole should we wish to go there. The axiom of choice, I think I put that in a footnote here in my lecture notes. It basically just says, well, if we have a decomposition of some set omega, in this case the unit interval, then we can construct a set by choosing one element of each of the pieces that we broke our original set into. Seems reasonable enough, but it is an axiom and we have to just assume it. It's typically assumed when you do measure theory this way. Otherwise, but there are, I believe, other approaches to measure theory that don't assume the axiom of choice, and then you get your, other headaches that seem to arise. I'm pretty sure somewhere out there, there's something where, like, if you don't assume the axiom of choice, then I think you can somehow get more Lebesgue measurable sets or something, but then there's other issues that go wrong. Like, nothing's really perfect here. So I'm not going to go down this rabbit hole right now. I just want to say that we have to assume that we can choose one of these elements. That requires us to assume the axiom of choice, and this is very standard in most classic approaches to measure theory. I mean, if you pick up most of these textbooks, whether it's an analysis textbook or a probability textbook, they're probably going to be assuming the axiom of choice. If you want, you can look at ways around that, but that's the way we're going to do it in this course. So we are a pro-choice course, I guess. Anyway, assuming the axiom of choice, we can construct this set H. What do we do with this set H? Well, the point here now is that no two points in H are equivalent. So H is constructed in such a way that if I take any two unique points from that set, they're not going to be equivalent, which means their difference, it hasn't fallen off the top of the page yet, their difference will not be a rational number. And this implies that if I have R1 and R2 rational numbers, then H plus R1 is not equal to H plus R2 unless R1 is equal to R2. So I take this set, if I shift it by R1 and I shift it by R2, if those are two different rational numbers, I'm going to get two different sets out that are, I say they're not equal, but I think strictly speaking, they should be disjoint as well. Yeah. Actually, H plus R1 intersect H plus R2 is going to be the null set for R1 not equal to R2. That's going to be important because it means, therefore, that we can write the unit interval as an infinite union, a countably infinite union R in Q of H plus R. This is a countable disjoint union of sets that we can use to get to the entire unit interval. Therefore, by countable additivity, what do we get? Well, we get that, well, 1 is equal to the Lebesgue measure of this unit interval. And furthermore, because it's a measure, it's countably additive, that implies that it's equal to the Lebesgue measure of this countable disjoint union, which means it's equal to the sum over all rationals of the Lebesgue measure of each of these H plus R's. Okay. And furthermore, all of these H plus R's have the same measure to them because of the argument from above that Lebesgue measure is translation invariant. Since Lebesgue measure is translation invariant, lambda H plus R1 is going to equal lambda H plus R2. So this is now a contradiction. Why? Why is it a contradiction? Well, what we're basically saying is that 1 has to equal the sum of an infinite sum of some value, which is going to be lambda H. And this means that if the measure of this set is 0, then we get 1 is equal to 0. Well, that's bad. Contradiction. Okay, well, maybe if the measure of this set is greater than 0, that's going to work. Well, that doesn't work either, because then we're adding up a positive number, an infinite number, a countably infinite number of times, and we end up with 1 is equal to infinity, also a contradiction. So the only conclusion that we're left with is that the set H is not Lebesgue measurable because we can't assign it any number, any measure, and have it make sense. What in the world does H look like? Oh, try not to think about it. It's going to be rough. Right? It's a strange set. You're taking it's uncountably infinite, right? Because you have uncountably infinite many equivalence classes that you're selecting one element from and putting them into H. It hurts to think about. But the point is, yes. So, conclusion is that the set of Lebesgue measurable sets is strictly contained within the power set. The power set, again, being the set of all possible subsets of the unit interval. Good times, right? I love this course so much. Okay, we have our one little fun fact here. And then we're going to do a couple little bonus material to finish out chapter 1 of this lecture notes that I'm putting together. So the fun fact is that Lebesgue measure on R is the only translation invariant measure. Which means exactly what we were talking about above. If I take the length of if I take an interval and I shift it to the left or I shift it to the right, the length, the Lebesgue measure, doesn't change. The same happens if we're working in Rn. Same for Rn. But what's neat is not so much that it's translation invariant, but that it's the only translation invariant measure, which means that every other possible measure would have to, well, not be translation invariant. So that's kind of cool. Furthermore, there is no infinite dimensional Lebesgue measure. What I mean by that, no translation invariant measure. This is kind of cool. If you're working in an infinite dimensional space, there is no translation invariant measure. There's a Wikipedia page you can look up. I put a reference in my course notes here about infinite dimensional Lebesgue measure. The idea is that you can't do it. We're not going to get into those proofs at the moment. But it actually is a very tricky thing when you're working with, say, stochastic processes, when you're working with function spaces. These are things that show up both in analysis, well, in not both, but all of analysis, probability theory, but also statistics, right? If you're looking at, say, functional data or statistics with stochastic processes, you don't have Lebesgue measure anymore. That means you're not going to get your probability density functions. Things like likelihoods don't exist, right? It just becomes a headache, right? But a fun headache and something that's really interesting to do research in. But we'll save that for another day because we still have time left in this lecture and we have 2 more topics to briefly discuss, which is product measures and independence. All right, so before we end today's lecture, I want to talk about 2 other topics very quickly. The first is just a general introduction to product measures. We're going to do this more in the next section once we have, well, knowledge of what an integral is in this measure theory context to work with. But roughly, I do want to just kind of talk about product measure in the context of Lebesgue measure. So for lambda, or maybe I should say it this way, we construct lambda on R by considering the, well, intervals, these half-open intervals A, B, and finite unions of them, and sigma fields generated by them, etc. For R, what notation am I using? P. Probably P for number of parameters, thinking like a statistician, right? We can do the same thing with P dimensional rectangles. There's a couple different ways to get to this, right? We can say, for example, if I could consider taking A, B, and crossing it with C, D, and having not an element, but a subset of R2. Right? If I just have, say, A and B, and I have C and D, then we can just kind of dot this out. And what we would end up with is a rectangle which is closed on two of its sides, and we'll use dots to indicate that it's open on the other two sides. And this can be extended into higher finite dimensional spaces, Euclidean spaces. So what's the measure of that thing? For what we really want to do is we want, right, the measure of this to be the volume. So we'll say lambda with a little 2 here to indicate that it's two-dimensional Lebesgue measure, though I might end up dropping that notation in later lectures because I think it's going to be a little cumbersome. And if the dimension is assumed, then it doesn't really matter. But if we, not equals, if we want to get the measure of this thing, AB crossed with CD, then it's going to just be the area, right? It's going to be what we want it to be, is we want it to be the area, B minus A times D minus C, which in this case is precisely the Lebesgue measure, the one-dimensional Lebesgue measure of AB times the one-dimensional Lebesgue measure of CD. Cool, right? So basically what we're doing is we're taking the Lebesgue measure of each interval and we're multiplying it together to get the, well, Lebesgue measure of the two-dimensional object, in this case a rectangle. And yeah, all I'm really doing is saying length times width is equal to area, right? There's nothing really going on here. But the idea is that we could do this for very general sets, Lebesgue measurable sets, and also other measures too. So it turns out, note the set of such rectangles in, we'll say, RP, where instead of multiplying, say, or crossing two intervals, I cross P intervals together to get a P-dimensional rectangle, which is half open and half closed. The set of this form a pi system. Cool. So now we're back exactly what we're doing. We can do the same thought again, right? We can do Dynkin pi lambda. We can do Carr-Theodori extension theorems, all this stuff that we did before. Yeah, and it's translation invariant. I already mentioned that in the previous rant before I got to this product measure section. And like I said, I don't want to go into more details on this because we'll talk about it more when we can do integrals and we can integrate out things and we can talk about that. But I do want to mention that generally, what we're interested in is that for two measure spaces, for two measure spaces being, I'm going to use script, which way do I do it? Oh, bold X for the space. We'll do X, script X, and mu for the measure. And we'll do bold Y. Which way should I do the bold Y? Like this? Or should it be more like, which one looks better? We'll do it like that. Bold Y, script Y for the sigma field, and nu for the measure. So the idea is if I have two different measure spaces, space X and space Y, I want to consider the product of these two spaces. So basically, we can define the product space where what I would do is I would take the two spaces that I'm working in and cross them together. I would take the two sigma fields, cross them together, and I'd get a new measure out, pi. And then what's pi? Well, where pi of A crossed with B is going to be the measure of A, mu, from X, and nu for B, for A in the X sigma field and B in the Y sigma field. Yeah, and that's more or less the whole idea. The idea is that we can rigorously define a product measure space. And again, we will talk about this more in later lectures. But it is a useful tool to kind of start with something like the real line and then build up to like p-dimensional spaces. This actually leads to one other interesting question. Which is, how are these related? And what I mean by these is two things. We have the Burrell sets on space X crossed with the Burrell sets on space Y, or we have the Burrell sets constructed, I do want this, constructed on the product space X, that's a terrible bold X, let's try that again, X crossed with Y. So these, on the surface, are slightly different objects. The first one says I'm going to take any Burrell set in X, any Burrell set in Y, and then product them together to get a space of sets. The second one says I'm going to consider the entire product space, and now I'm going to construct the Burrell sigma field on that product space. Are these two things the same? Are they different? Well, I'm not going to prove anything right now, but I will cite Dudley's textbook once again in chapter 4. I have proposition 417 written down in my notes here. So we'll say from Dudley, Dudley, L-E-Y. This is 4.1.7. The claim is that the Burrell sets on X crossed with the Burrell sets on Y is contained within the Burrell sigma field generated over the product space. But these two are, I'll say usually, because that doesn't make any sense mathematically, equal to each other. What I mean by usually equal to each other is that in many of the nice settings that we will do in like this class and most textbooks, you're going to have them be equal to each other. For example, if x is equal to y is equal to the real numbers. In that case, these two objects, the product of two Burrell set, the Burrell sigma field or the Burrell sigma field generated on the product space are going to be the same. This goes down another wonderful mathematical rabbit hole. I put another footnote in here that this, more precisely, we'll say equality occurs when x and y are what's called second countable. I will leave it to you to go look that stuff up if you really want to. Or you can just be happy with the fact that most of the, I guess strictly speaking, I should say the measurable spaces are second countable. Yeah, I'm going to leave it to you to look that up should you like it, or you can just assume that, okay, in the nice settings that we will consider in this course, like the real number line, it's not going to matter. They're all going to be the same thing. But yeah, you can go down some pretty dark rabbit holes in analysis where things start to break down in horrible, horrible ways. And on that note, let's talk about one more special topic before we end this chapter and move on to integration in the next lecture. And that's going to be the idea of independence. And this is pretty cool because this is like actually probability. I've heard it said by people smarter than me that probability theory is basically measure theory with independence. That's one way to think about measure theoretic probability theory. Because so far we haven't done any real probability theory, we've just done measure theory, but independence is kind of a special property that we can impose on a sigma field. That's what we're going to do here. So we need a definition. What in the world does independence mean in the context of measure theory? This is going to be a definition: independence for sets. And that is for a countable collection of sets AI, where we're going to have I in some index I. It's countable. We could say, I guess, 1 to infinity, but I just do it this way. So for a countable collection of sets, we say that this collection is independent if what? Well, if for all finite j contained in I. So if we have a countable collection of AIs. If we pick a finite number of them, if we pick any finite number collection, subset of them, we have that the measure mu. Did I define a measure space here? Okay. Let's give myself, am I getting a little bit of room here? It's kind of lagging. Let's just define, I feel like for every single section of this course, we always have to start the same way, which is let omega f mu be a measure space. We'll just sneak that in there so that we have a general measure space to work with. Now, and the A's would then be an F so that they would be mu measurable and all that and everything. Anyway, the point is that the measure of the finite intersection of the AJs is going to equal the product, the finite product of mu AJ. So this thing here in green is basically the definition of independence for sets. These sets can be thought of as events that would happen, and this is a very standard notion of independence, right? If A1 and A2 are independent of each other, then the probability of them both occurring is the product of the probabilities of each individually occurring. Let's do an example. Let's draw some cards. How about that? The example is going to be, I have my 52 cards, right, in my deck. The event A1 is going to be draw a red card from my 52 card deck. A2 is going to be draw a, I think, heart or club. In case you're not a card player, hearts are red and clubs are black. And that's half, each of those events will correspond to half the deck. And A3 is going to be, draw a queen. So the point is that this collection of three possible sets, it's all discrete probability now, so we don't really need measure theory, but nevertheless, the idea is that these three events, the collection of sets is going to be independent. And we can show that by basically just writing out all of the probabilities of this occurring, which, let's just do it for fun. I like drawing cards. So if we consider the probability of drawing a red card off the top of the deck, well, that's 1/2. If we consider the probability of drawing a heart or a club, that's also going to be 1/2. And if we can, no, that's 2. And if we consider the probability of drawing a queen, well, there are 4 queens in a 52 card deck, so that's a 1 in 13 chance of getting a queen. Now, if we start considering intersections, we could say, well, what's the probability of getting a red card that is also a heart or a club, which basically means what's the probability of drawing a heart? That's 1/4, which happens to be 1/2 times 1/2. That's good. We could ask the question, what about a red card that's also a queen? Well, there's 2 of those in the deck, so that becomes 1/26, or 1/2 times 1/13. That's good. Similarly, A2 intersect A3 is also going to be 1/26 because, well, there's a queen of hearts and a queen of clubs. And if we intersect all 3 of these events together, there's only one possible outcome. And that is the queen of hearts. 1 in 52 chance. So this means that these 3 sets, this collection of sets, is independent. But again, this is discrete probability. We don't really need measure theory for this. But for measure theory, now what we're going to talk about are independent sigma fields. Let's define that. All right, so we can define independent sigma fields. Independence for sigma fields. Because we couldn't just end it with cards, right? This is a measure theory class. For a countable collection of sigma fields. What we'll define those as script f sub I contained within some greater sigma field that contains them all. I in I. We say the collection of sigma fields is independent if what any set of sets AI is independent. Yeah, any set of sets AI where we pick each AI from an fi I in the index set I is independent in the sense of what we talked about above. So what we're doing is we have our countable collection of sigma fields. We're going to go in and we can take any AI from fi, that is, we go to f1, we pick an a1. We go to f2, we pick an a2. For any choices of these AIs, we can construct this set, and this set must be independent in the sense of the independence that we talked about up above. Okay, so that's kind of a cumbersome definition, right? Luckily, we can go back to the notion of a pi system to make this easier to work with, right? Because if you work with that definition, it's like, how in the world am I going to check independence if I have to check every single possible way of choosing sets AI from fi for all I in some countable index set, right? That's horrible. Luckily, we have a theorem that's going to help us. The theorem says, let script A1 and script A2 be contained in the sigma field F. Let these contained in F be pi systems. Once again, Dinkin pi lambda for the win, right? But we haven't stated the theorem yet, so let's not get ahead of ourselves. If we have two pi systems that are contained within the same sigma field, or let that be the case, if the measure of the intersection of A1 and A2 is equal to mu A1 times mu A2. This is for any A1 in script A1 and A2 in script A2, then the sigma fields generated by A1 and A2 are independent. Cool, so once again, we use the power of the pi system to say that all we really need to do is make sure that these two pi systems are independent, and that will imply that the sigma fields generated by the two pi systems are also independent. Let's prove it. All right, this proof is actually pretty short. It's something that, given the hint that you need to use the Dinkin pi lambda theorem, you could probably do yourself, but we'll just do it now. There'll be plenty of horrible little homework problems coming from the textbooks, so we won't worry about that. Anyway, we'll say let's say fix. Step 1, fix an A1 in script A1. And define two measures these two measures for sets B contained in F, the sigma field that contains everything we're working in. That's like the super sigma field that contains all of these sub pieces that we're interested in. So we're going to define two measures. We're going to call nu1 of b to be mu of a1 intersect b. And we're going to call nu2 of b to be mu of a times mu of b. Right. So we have two measures. What do you think we're going to do? We're going to show that they coincide, right? And if they coincide, then if we extend them to a sigma field, Dynkin pi lambda, uniqueness of extension, they're going to be the same thing. And that means that mu of a1 intersect b is going to equal, this should be a1, mu of a1 times mu of b1, or just b. So that's the idea. We want to show that these two things are the same. By assumption, we have that nu1 of a2 is going to equal nu2 of a2 for any a2 in script a2, right? That's basically the first line, the second line here of the theorem. If these two things are equal for a1 and a1 and a2 and a2, so we know that's true. And then we're basically done, because we'll say then by uniqueness, uniqueness of extension, nu1 and nu2 have to coincide on the sigma field generated by a2. So that means that therefore mu of, yes, I see how I'm doing this, a1 intersect, we'll say b2, has to equal mu of a1 times mu of b2 for any b2 in the sigma field generated by script a2. So we're halfway there, right? We're fixing a1, and we're showing that it holds for any element of the sigma field generated by a2. Now we'll say now, do the same thing. Do the same argument again, but by fixing some b2 in the sigma field generated by a2. To get that mu of b1 intersect intersect b2 is equal to mu of b1 times mu of b2 for any, in this case I'll just write shorthand bi in sigma a I equal 1 or 2. So you just do the same argument again. This time you fix an element of the sigma field generated by A2. You do what we did above, pi lambda, uniqueness of extension, etc., and yeah, we're done. QED box. That's always nice. So what was it is worth just looking at this proof very quickly before we end this lecture video. What we started with was just A1, script A1 and script A2. These are just pi systems. Then we fixed A1 and we turned A2 into the sigma field. We kind of rose it up. And now we can work with the entire sigma field generated by A2. Then we fix an element of the sigma field in A2. We let the other one, A1, vary up to a sigma field. And now we're up here where we have sigma field A1, sigma field A2, and we have this measure coinciding on the sigma fields. And since the two measures coincide, nu1 is equal to nu2, that means that mu, the mu of the intersection is the product of the mu's. So I think it's kind of neat the way you can do this, right? You can define two measures that a priori don't have to be the same thing, but then you show by uniqueness that they do in fact have to be the same thing, and that proves the theorem. Very cool. So these were all the lectures that I have planned for the measure theory, the intro to measure theory bits. So just to recap, we talked about general definitions, we talked about Carathéodory extension theorem, we talked about the uniqueness of measure, of the extension that is, and we talked about Lebesgue measure and some extra things like product measure and independence. The next topic we'll be doing is about maybe 3 or so lectures, we'll see how long it takes, on integration theory, because this is the next big piece of this course, which is now that we have this idea of a general measure, we want to use it to do integrals, and more general integrals than what Riemann was doing back in the 19th century, right? Because we're in the 20th century, well, technically 21st, but in this course, we're talking about Lebesgue. We're talking about early 20th century mathematics and how in the world do you do integrals in sort of a more general setting. That's going to be the next topic. And like I said, it should be about 3 lectures or so. We'll see how that goes. And I'll see you in those lecture videos. Have a good one.